Thanks, Anio, and thanks for having me. It's really good to see all of you guys here. This is actually my first MFEM workshop, so very excited to be here and to learn about all the exciting things that are going on inside of MFEM. Some applications that I didn't know were actually possible in MFEM. So um, we are the space-time guys here at Penn State, and I'm going to be talking about one of my favorite topics, which I'm sure is your favorite topic as well, which is quadrature. Um, and some of the issues that come up with quadrature when we try to go into higher dimensions. All right, so here's a brief overview of my talk. I'll be giving an introduction, some background about quadrature. We'll be talking about primarily simplicial quadrature, although I will say some controversial things about quadrature on cubes as well. So don't worry. If you're not offended yet, you will be offended later. Then I'm also going to be talking about what I think are the best practices for quadrature and simplices, and then talk about some more general topics related to quadrature when it comes to choosing quadrature strength and coming up with adaptive quadrature procedures. And then the last part is just like open research problems that someone needs to solve. And also someone needs to find money to solve. So, all right. So this talk assumes that you know almost nothing. So what is a quadrature rule? We say it's a procedure which numerically approximates the integral of an L1 function on a compact domain using a weighted sum of the function values at a particular set of points. I said compact domain, I mean closed and bounded domain. Honestly, if you want to, it doesn't have to be a bounded domain, but for the purposes of most finite element methods, since your elements are finite, they'd better be bounded. Okay, so then of course the weights are quadrature weights for your rule. The points, which are the xi's, they're the quadrature points. The combination of the weights and the points are a quadrature rule. Some authors like to make a distinction between quadrature and cubature, and they use quadrature to refer to numerical integration procedures on 2D domains, and they use cubature to refer to integration procedures on 3D domains. We will not be doing that here because we have to go to higher dimensions, and that terminology does not work in higher dimensions, okay? So we refer to everything as quadrature. Everything that's a numerical integration procedure in any number of dimensions, that's quadrature. And cubature is something else. All right. Desirable characteristics of your quadrature rules. These are desirable in my eyes. The first slide, that will be offensive. So your rule should exactly integrate some polynomial of a particular order P. Your rule should, if possible for efficiency purposes, have a minimal number of points. All your points should lie within your domain of integration. This is actually surprisingly something that is not true of a lot of the rules that are in the literature. Not sure how that slipped through. Your points should be symmetrically distributed. This is probably the most controversial point here. They don't have to be symmetrically distributed, but for some reason, engineers have an aesthetic preference for things that are symmetric. This is very hard to convince them to use things that are not symmetric. So if you want people to use your rules, they kind of have to be symmetric for cultural reasons. And then all your weights should be positive. There's an example of a couple of quadrature rules. The one on the right is symmetric. The one on the left is not symmetric. And the points are actually, the sizes of the points vary due to the fact that they've been increased in size or decreased in size based on the associated quadrature weight. Okay, so it's like a fancy way of visualizing your quadrature rule. All right, so how do you satisfy all 5 of those properties? It depends on the geometry you're trying to integrate over and the ambient dimension that the geometry resides within. So for 2D domains, you have quadrilaterals and triangles. 3D domains, hexahedra, tetrahedra, square pyramids, triangular prisms. And 4D domains, we're interested primarily in tesseract, pentatopes, cubic pyramids, and tetrahedral prisms, where the tesseract, of course, is just the 4D extension of the hex. The pentatope is the 4D extension of the tet. And then cubic pyramids like a square pyramid, and tetrahedral prisms like a triangular prism. Okay. So basically, you can think about these as just hypercubes, simplices, and associated tensor products. You can tensor product basically any two things that you want. All right. So we'll primarily talk in this conversation about hypercubic and simplicial quadrature rules. So here are like probably the most popular procedures for integrating on the hypercube. You can use Gaussian quadrature rules where you take tensor products of 1D Gauss rules. And these, of course, satisfy all your desirable properties except that you have too many points. Okay, suboptimal number of points. There's also these Smolyak quadrature rules. That's definitely not how you say it, but that's how it's been said to me. And you downsample your tensor products, and you still get the same order, but you have less points. These are still suboptimal, but in very high dimensions, these get used a lot. And then, of course, custom quadrature rules, where you just solve an optimization problem, and you satisfy all the desirable properties, but you have to construct them on a case-by-case basis, and that could take a lot of time. Okay. And then for simplicial quadrature, you have very similar rules. You have the Gaussian quadrature rules again, where you just do tensor products, but then you use a Duffy transformation to map the cube onto the tet or onto your simplex. These are going to, again, have a suboptimal number of points because they're just based on the Gauss tensor products, which had a suboptimal number of points on the cube. So you haven't really gotten away from anything there. There's these rules that are like the Grundmann-Moeller rules, which are based on combinatorial identities. Very clever bit of math, but does not work very well, as we will discuss later in this presentation. And then custom quadrature rules, which are, again, you just solve an optimization problem, and you just try to like find the best possible rule with the minimal number of points. Okay. Okay. For our applications, we're primarily interested in simplicial quadrature, although I think most of the audience here is very, very preferential towards hexes for reasons that I'm sure are very good. So in our cases, we're interested in just very rapidly generating meshes in the vicinity of complex geometries for aerospace applications. And so in our case, usually that's done with some Delaunay meshing or advancing front techniques or hybrids thereof. And so we want to work on simplices. Also, there's a very well-developed class of anisotropic mesh adaptation techniques for simplices that extend into higher dimensions and have been extended into 4 dimensions by the guys at MIT. One of them who is sitting in the room over there and who's now doing quantum computing is Hugh. You can wave at Hugh. Okay. All right. So we're going to talk about what is used to perform simplicial quadrature in MFEM right now. All right. So one of the primary ways of integrating things in MCRIM on a simplex is to use the Grundmann-Moeller rules. This is one of the primary options. So if you go to /FEM/intrules.cpp, you will see a very efficient implementation of these rules. Okay. These rules are taken from the 1978 paper entitled Invariant Integration Formulas for the N-Simplex by Combinatorial Methods. This paper is incredibly clever. They, in fact, construct like a symmetric or an affine invariant polynomial basis on the simplex. And then they use a series of like combinatorial identities to prove that the quadrature procedure that they construct has a remainder of 0 for certain classes of polynomials with degree less than like 2s plus 1. So it's almost like an attempt to construct like a Gauss quadrature rule, but a symmetric Gauss quadrature rule on a simplex. So it's very nice. There's one teeny tiny problem with these rules, that they tend to be numerically unstable due to cancellation errors because they do admit negative weights. Now, this is gonna, if you have negative weights, some combination of negative and positive weights in your quadrature rules. I guess if all your weights are negative, then you're fine. Although Don't really know how you're going to get positive areas. But okay, if if you have a combination of positive and negative weights, then obviously you can have cancellation errors. And this problem gets worse as you go into higher dimensions because you have more points, more quadrature points you have to use for a given polynomial degree. And the number of points generally will increase exponentially as you go up into higher dimensions. Okay, so from our perspective, you should not be using these rules in higher dimensions unless you want to die by 1,000 cancellation errors. So you might ask yourself, are cancellation errors really a big deal? Or is this just like fear-mongering by the numerical methods elite? These are questions you can ask. Okay, so honestly, it depends on your application. So the corrupting influence of cancellation errors is most clearly seen when you're trying to do order of accuracy studies, where your total numerical error is driven to relatively small values. So if you have a very small error tolerance, then this is going to be very important for you. And if you have a very large error tolerance, then you're safe. You have other things to worry about. So we found that when we were using the Grundman-Moeller rules in 4D for our applications, if we try to do order of accuracy studies with polynomials starting around order 2 or 3, that we actually will get our error to stagnate, okay, and we won't actually be able to recover the expected order of accuracy, okay. Andreas Schaffelner, who initially, I believe, was working in the 4D branch, also ran into the same issue and had to use a different set of rules than the Grundman-Moeller rules that are default implemented in MFEM. So if you learn nothing else from this presentation, it's don't use these rules under any circumstances if you're doing an order of accuracy study in dimensions greater than 3. Okay. Otherwise, your implementation will magically work for first order and second order and then stop working for third and higher orders, and then you'll spend several months trying to figure out why. All right. So there's very serious cancellation error examples that you can look at. The most classic one is just Wilkinson's polynomial that I think most people in this room are familiar with, where Wilkinson constructed this absolute disaster of a polynomial that involves products of these factors here up to 20. And then if you actually expand this, and I did check all these coefficients, so all these numbers are correct. If you like the slide, yeah, I checked by hand. I LaTeX this by hand because I have a lot of free time. If you plug in any value of x and you attempt to evaluate this expression, you'll note there's positive and negative weights here that will cause this expression to just say the result of your computation will be unreliable. If you have some time, I recommend plugging this into MATLAB and trying to evaluate a root of this. It's a lot of fun. You will get, in most cases, you'll just get a nan. But then you evaluate this and you're fine. It's perfect. Okay, so cancellation errors are important. Here's an example what the Wilkinson polynomial looks like when it was computed using this method. And the example of what it looks like when it's being computed using the expansion is probably this blank space next to this plot. Okay. All right, so now I need to sell you on some custom quadrature rules. So many custom quadrature rules for simplicists already exist in 2D, 3D, and 4D, even in higher dimensions than that. And most importantly, the most important thing about these rules is that they have positive weights. So they overcome the deficiency of the Grundman-Moeller rule, and they also exactly integrate a polynomial of a particular degree, and they're symmetric, and they have all the points inside of the domain, et cetera, et cetera. So they satisfy all of our requirements. All right. So best practice quadrature rules and simplicists, in my opinion. All right. We have to start with rules that I am affiliated with, even if they're not good. There's some rules that were developed at Stanford by Schoon, Ham, and myself. These quadrature rules are for 2D and 3D simplicists, and they have the added feature that not only do they integrate polynomials of a particular degree, but they also contain a triangle or tetrahedral number of points. So if you want to use If you're using like some collocation finite element methods and you want to like under integrate because you want your finite difference and finite element methods to look very similar for some reason, then you can use these points. You'll note that this exactly represents a polynomial of degree 3, like with this set of points here. Okay, so they're based on these close packed lattice arrangements. And then in the vertical column here, you'll see like the dimension. So this is for triangles for this first row here. Tets are in the second row. And then we have on the, like up here, you have the degrees of the polynomials that they can exactly integrate. And you can see that for triangles, we develop rules all the way up to 66 points, exactly integrating a polynomial of degree 17. And then on tets, we did it up to degree 9 with 84 points. Okay, so these are not optimal, but they're very useful if you're interested in exactly being able to not only integrate, but also represent a polynomial with your integration points for some reason. So there's certain very exotic finite element methods where that's useful. Okay, so that's why these rules exist. And then somehow the community found them and started using them for other things, which is not what I recommend, but that's what they do. Okay, then the gold standard rules are these Witherton and Vincent rules from 2015 that were generated with this code called polyquad. These have the fewest points to date and go on triangles all the way up to degree 20 with 79 points. And on tets, they go all the way up to degree 10 with 81 points. Then, because 2D and 3D are not enough, the title of the talk was 4D and beyond. There's the rules that I constructed with Dharmafal and some of his students. So these are exactly capable of representing polynomials in 4D and exactly capable of integrating, in this case, a degree 8 polynomial with 126 points on the 4 simplex. And then there was a set of better rules that we came up with in this paper from 2021 using a modified version of polyquad that is not in the public domain. And we can integrate up to polynomials of degree 16 with 1,055 points on the 4 simplex. Okay, the first 9 of these rules are the best rules to date. And then the last like rules, I think 10 through 16 have been superseded by these guys. And so I think these guys are based out of Russia. They actually went all the way up to dimension 6. So simplices 3 through 6 and degree 8, okay, with 553 points. And that wasn't enough. That was the conference paper. The journal article, they went even crazier. And so if you want the best in class rules, especially for higher orders beyond degree 10, then I recommend you take a look at this paper. As a plug of our rules over their rules, our rules are contained in a very nice text supplement document. Their rules, you have to download their code and then run it, I think. So, all right. So it depends on how lazy you're feeling. Okay. So this is all well and good. That's the state of the art when it comes to quadrature rules and simplices. You can get rules all the way up to dimension 6 and degree 10. So very high quality rules exist that are custom for most of the applications that people in this room are interested in. Now, this still leaves a very important open question, which suppose that you want to choose a particular custom quadrature rule. How do you know that your custom quadrature rule is strong enough? The simple answer that most people will take is, well, they'll say, well, I have a relatively simple PDE. Maybe I'm solving the incompressible Navier-Stokes equations, and I have a nonlinear convective term that looks like this with a test function W. And so I look at the maximum order of this term, and if this is degree P, then the total term is like degree 3P minus 1 if I have straight-sided elements. And then maybe I just add a couple of extra degrees for safety, and 3P plus 1, or 3P plus 2, depending on who you're talking to. So this strategy, of course, works very well for simple PDEs that have very simple nonlinear terms. However, if you have ratios of polynomials, you have rational functions that show up, and you're trying to integrate those, like you have some nonlinear fluxes that have rational functions in them, then this is not a very good answer. So what can you do that would be better than that? And the short answer is that you should probably adapt. And so you can, of course, just introduce a high-resolution quadrature rule and a low-resolution quadrature rule, where high resolution, low resolution is just determined by the number of quadrature points the rule contains. And then you can compare them, compute some estimated quadrature error, and then continue to increase the strength of your low resolution and high resolution rules until your estimated error drops below some user-defined threshold that you have. Okay, so this is great. So the question is, how do you construct, on simplices, how do you construct your high degree quadrature rules or high resolution quadrature rules? Well, one is you can just increase the number of quadrature points by choosing a rule that integrates a higher degree polynomial. So this is what we would call in finite element methods P adaptation. Just boost the ability to represent some function. So in this case, you're boosting your ability to integrate some function. This strategy works very well if your function is locally smooth. However, what if your function's not locally smooth, because it usually isn't? Then in that case, you should probably do something closer to H adaptation, where instead of just increasing the strength of your rule, you should be subdividing your element and then using the same low order rule on each of the subdivisions. Okay. All right, so you can of course take a tet, subdivide it into 8 subtets, and then use this rule on each of those 8 subtets. I've only showed the rule on one of the subtets because I did not have time to fill in the rest of them. Okay, and this works really well if your function is like locally discontinuous and you want to zoom in onto what the exact integral of the function is on your subdomain. All right, now some of you guys have immediately noticed the problem with this approach is that if you use an adaptive quadrature process, and it requires a significant number of function evaluations, because you're going to be evaluating both the weak rule and the strong rule, the low resolution and the high resolution rule, and you're going to be using this or doing these evaluations within some sort of recursive process. Okay, so that's a lot of function evaluations potentially to get to whatever your threshold is, especially if your threshold is somewhere near machine zero. Okay, so ideally you would like to reduce the number of function evaluations, and the solution to that is to use some sort of nested quadrature rule. So these things, of course, exist in 1D, and you can take tensor products of them to generate higher dimensional nested quadrature rules. But to our knowledge, they do not exist on simplices. So that's an open area of research, is to say, okay, I have a quadrature rule here, and then it contains, as a subset of its points, a lower degree quadrature rule, and I can compare the two values that I get from evaluating those quadrature rules and get an error estimate. Okay. So this would be like the holy grail in simplices, if these rules existed, which they don't. Okay, at least not to my knowledge. All right, so some things for people in the room who have time and money. The first thing is try to come up with some nested quadrature rules on simplices in basically any dimension that's not 1D. So dimension 2 and above. The second thing is we need higher order quadrature rules on simplices in dimensions 5 and above. Like the rules right now just end at degree 10. And for rational functions, degree 10 is not very good in some cases. And then there, as far as we know, no custom quadrature rules in dimension 7. And it turns out there are some interesting applications in dimension 7. I can't speak to dimension 8, but dimension 7, I think the previous authors quit just one dimension too early. So there's some opportunities there potentially to construct some quadrature rules on 7 simplices. All right. So I have no idea how much time I took, but that's the end of my talk. So thanks for your attention.
Thank you very much for the interesting and entertaining talk. Any questions?
Yes, Hugh.
When are you going to put the Witherden rules into MFEM?
Okay, so we put some of our rules into the 4D version of MFEM. But yeah, we could put all the Witherden rules into MFEM, and that would be probably very helpful. I should mention that for those of you guys who use tensor products, you are not safe because as you go into higher dimensions and you take tensor products of Gauss rules that have small weights, like say 10 power minus 1, 10 power minus 2, you'll note that 10 power minus 2 multiplied by itself 6 or 7 times gets you down to machine zero very rapidly. So tensor product rules in higher dimensions are extremely risky if you're not paying attention to what you're doing. That was not your question, but I thought I should mention that.
Integrate carefully. Any other questions?
So I didn't know about these quadrature rules where on the simplex where the points kind of coincide with the degrees of freedom. You can make at least in like the count, right?
Oh yeah, yeah.
So I mean, we have that on quads, right? You can use Gauss-Legendre points for your degrees of freedom, and also they are a quadrature rule. And it seems with the rules that you guys invented, that happens on simplices.
Yes, it does.
So it's a nice, very nice property that I didn't know. It's a comment more, but yeah.
Yeah, I used them during my PhD, so I thought they were nice. But yeah, there's for certain methods it's helpful. Some people though they don't like to evaluate their functions at the same quadrature points that they used, interpolation points they use for their solution representation because they feel like they need to like triple or quadruple that. So I guess it depends on how nonlinear your problem is. But
Actually, this could be very interesting and useful. That's one of the reasons LOR, this lower refined method, works on quads, because the degrees of freedom are a good quadrature rule.
oh, okay. Yeah, we should talk about that.
And just one comment on the negative coefficient. One of the things that you will very commonly experience in MFEM is you get a negative norm. And you get a negative norm because the function is zero in all quadrature points except the one that has the negative quadrature weight. So that I think a lot of us have experienced. Okay, any other questions?
Oh, wow. Okay.
Okay, this last two and then we have to move on.
You mentioned earlier that you include symmetric in your desirable properties because of engineers.
Yes.
Right?
That was kind of a joke. I also have more concrete reasons than that. So when we're trying to solve the optimization problems, having symmetry allows us to group the points into orbits, and then that significantly reduces the size of the optimization problem that we have to solve. So that's an added benefit of choosing symmetric rules. And there's also some arguments that some people make about, oh, well, if you have symmetric quadrature rules, then you'll never introduce any numerical asymmetry into your solution. I am not very convinced by that because you're already operating on a simplicial grid, and that thing's not symmetric usually anyway, but okay. But it's really more, I would say, more for efficiency of optimization purposes than it is for any particular engineering aesthetic reason.
Okay, thank you.
Yeah.
Well, I mean, there's a very practical reason, which is to be independent of the ordering. You don't want to, if you renumber the vertices of your mesh, to all of a sudden have completely different.
Oh yeah, you'll
spaces.
get a different answer as well. Yeah. Yeah, I don't like that, but yeah, some people don't mind.
So yeah, I guess I have questions about these co-location of quads and DOFs. Do these quadrature rules that you come up with, do they also like have like faces which share quadrature rules with like a triangle or I guess lower dimension geometry?
Oh, are they like nested in that way?
Yeah.
No.
Okay. Ever thought about ways
Too bad.
But yeah, yeah, you could create like a simplicial like Gauss-Lobato type rule, which would fix that problem.
Okay,
You can basically do anything because it's optimization. So.
we gotta move on.
All right, thank you.
Let's thank David again.